Great. Okay, well, thank you everyone for joining today. Our speaker today is Ryan Sanders. He's a Pebble Fellow at the University of California, Davis. He finished his PhD in 2018, working with Alice Shapley at UCLA. And today he's going to talk about galaxy metallicities and baryon cycling over the past 12 billion years. Thank you.
All right, thanks, Anna, and thanks everyone for the opportunity to speak at the seminar for many things associated with astronomy now. Can't remember what all was in the title. Yeah, glad to get to talk. I was scheduled for March 11th to visit last year and actually got a call while I was on the way to the airport to fly to Boston that the pandemic was shutting everything down. So that was a bit of a wild ride last year, but super glad to talk to people today and meet with some people at the CfA, even virtually, and hopefully over the next couple of years, make it out there in person at some point. So the work I'm going to show you today has been done in collaboration with a lot of great people I've listed on this slide, including the MOSDEF survey team on the lower left, and then Tucker Jones at UC Davis and some other collaborators down on the lower right. So before we, there we go. Before we jump in, I just want to do a definition of metallicity, since it means many things to many people. When I say this, I'm going to be talking about the gas phase oxygen abundance of the interstellar medium. And so this will be given by ZISM or by 12 plus log over H, which we add 12 to for some weird historical reason that makes it longer to write on our axis titles. So for a little motivation, I'm showing two simulations here. The one on the left is a dark matter only simulation showing the gravitational interaction of dark matter and the buildup of the large scale structure of the universe. And this is a very well-behaved process that's very well understood, and in particular, in-body simulations can do a fantastic job producing a realistic dark matter universe through these gravitational interactions and halo mergers. But on the right, we have a simulation from the illustrious TNG collaboration. And this is showing the baryons. So this is showing the gas interactions in a hydro simulation. And you can see that the interaction of the baryons is extremely complex. You not only have the infall due to gravity, but you also have gas that's being pushed outwards due to energetic feedback when this gas is processed during the process of galaxy formation. And so this big mess of complex processes in the baryon makes it a much harder a harder process to understand completely. And so there's a lot of gaps in our knowledge that we're working on improving of understanding how the baryonic processes that form galaxies behave in detail. Now, to take a more simplified view of what's going on in that baryon simulation there, we can look at a cartoon picture of a galaxy and just think about these key processes that are involved in the baryonic formation of galaxies. So we have accretion of gas from the intergalactic medium that moves through the circumgalactic medium. This feeds star formation within the disks of these galaxies. Processing of gas via star formation or black hole accretion yields energetic feedback that can drive outflows and remove material from the galaxies. You can even have higher order effects like gas recycling, where past outflows are reaccreted in later generations of accretion events. And so we'd like to constrain some very key and fairly simple parameters, such as the gas accretion rates and the gas outflow rates in these galaxies. But it's been very difficult to constrain these properties through direct observations of gas accretion or of outflowing gas. We can identify accreting or outflowing gas in observations of galaxies, but typically converting those observations to global accretion rates is very difficult and contains systematic uncertainties that can be an order of magnitude in size. And in particular, these observations of, for example, outflows are typically line of sight observations. And so converting that to a global rate is very difficult. And so as an alternative probe of this process, we can use the metallicity of galaxy ISM because each of these stages of this process actually modulates the ISM metallicity by either lowering or raising the metallicity due to diluting metals, removing metals, or adding metals if it's through star formation. And so in particular, the way that we probe this baryon cycle process with observations of metallicity is through metallicity scaling relations. And so we have relations such as the mass metallicity relation, which I've shown on the left here, and measurements of the mass metallicity relation at redshift 0, shown by the black line. And we can basically combine the scaling of metallicity with properties like stellar mass and employ chemical evolution models of galaxies to interpret this. So we can have very simple models like the closed box model, which has no gas accretion and no gas outflows. And so in this case, the metallicity depends on the gas fraction, which is constantly depleted because there's no gas accretion. And this term Y is the metal yield from supernovae for metal production through nucleosynthesis. And these closed box models produce metallicities that are far too high to realistically describe the galaxy population. And so it's not a realistic scenario. One additional step of complexity, we can add accretion to these models. So you can have what we call an accreting box model, where you accrete new gas, but there's still no outflows. This still depends just on the stellar yield and the gas fraction. The metallicities move lower because you have more gas coming in that can dilute the metals in the ISM, but you still can't produce metals low enough to describe a realistic galaxy population. And in particular, what we need are a class of models that are called equilibrium models, or sometimes bathtub models or gas regulator models. These are models that include both gas accretion and they allow outflows to remove gas from the galaxies. And so down on the bottom here, you can see that the metallicity depends on both the gas fraction and on this eta out term, which is the mass loading factor of outflows. That's the outflow rate divided by the galaxy star formation rate. And by combining these terms, you can produce essentially arbitrarily low metallicities based on how strong the outflows are. And so we have measurements of the gas fractions for galaxies at redshift 0. And so you can basically, tune your model until you find the scaling of the mass loading factor with stellar mass that can reproduce the galaxies. And so this gives us constraints on the properties of outflows in these galaxies that are quite strong. And so these equilibrium models are really our best tool to interpret these metallicity scaling relations. And those two terms, the gas fraction and the mass loading factor of outflows, highlight these two physical mechanisms that are really important for setting the gas phase metallicities in galaxies. So essentially the stellar yield from supernovae sets an upper limit on the metallicity that you can have in the galaxy. And there are these two mechanisms, one is metal dilution and the other is metal removal, that are key to setting the metallicities. So the metal dilution, the key parameter is the gas fraction. And essentially newly produced metals are mixed into a larger gas reservoir if you have a larger gas fraction, and thus the metallicity is lower. For metal removal, the key parameter again is the outflow mass loading factor. And outflows can remove newly formed metals from the galaxy instead of mixing them into the ISM. And it also regulates star formation, thereby slowing the production of metals. And so both of these effectively lower the metallicity. And so these two physical mechanisms, we'd like to know, how important they are relative to each other and how they're related in setting things like the mass metallicity relation. And so at redshift 0, there's been a huge amount of observations of these scaling relations. On the left, I show the mass metallicity relation from a recent paper from Mirko Kurti. And on the right, a 3-parameter relation known as the fundamental metallicity relation between mass, star formation rate, and metallicity. And both of these have been really foundational relationships in setting our understanding of baryon cycling and galaxy growth in the low redshift universe. We find that outflows are absolutely required to explain galaxies in the low redshift universe. And then this FMR on the right-hand side, we basically have this relationship where at fixed mass, galaxies with higher star formation rates have lower metallicities. And this is thought to reflect gas accretion and the metal dilution mechanism, where you accrete new gas, it drives the star formation rate higher while simultaneously lowering the metallicity. So it's a great piece of evidence of the impact of gas accretion. So we've identified these at redshift 0, but at higher redshifts, galaxies are actually really interesting laboratories to study feedback because they have higher star formation rates, presumably larger accretion rates from cosmological accretion. They have higher gas fractions, smaller sizes, and we see a higher incidence of strong outflows in high redshift galaxies. So all of this makes the high redshift universe a really interesting place to study these relationships, and in particular the baryon cycle, which we think was more vigorous at early times. And so big questions we like to answer is, what does the mass metallicity relation and the FMR look like at high redshift? And what physical mechanisms control their shape and evolution across cosmic time at multiple epochs? And so that's what I'm going to talk to you about today. So first, let's talk about the evolution of the mass metallicity relation from redshift 0, stretching out to redshift 3.3, which is about 12 billion years in the past look back time. So people have been studying the mass metallicity at high redshift for quite some time, for really the past decade and a half. And if we look at past results, there are some, general results that people find in common in the past. We find as you move to higher redshift, you find lower metallicity at fixed stellar mass compared to redshift 0. But the exact amount of that evolution varies from paper to paper. And we find that the slopes can vary quite a bit. Some of them are consistent with the slope that you find at redshift 0. Some of them find much steeper mass metallicity relation than at redshift 0. And some of the challenges that have affected previous studies and prevented essentially precision metallicity studies are small sample sizes and low spectral quality, where the signal to noise of emission line detections is not very good. Sample selection, in particular, having homogeneously selected samples that are representative. And now that we know that the fundamental metallicity relation exists, we know that actually being representative in star formation rate is key to being representative in metallicity, because metallicity depends on star formation rates. That's very important to have a representative sample. And then also in how the metallicities are derived. And this is a big one. So the choice of metallicity calibration you use to convert your line ratios to metallicities can greatly affect the resulting metallicities. So you need to be careful of this choice. And also the metallicity indicator, which is which line ratios do you use to determine the metallicities. And on the left here, I'm just showing this plot showing a past study of the mass metallicity relation out to redshift 3.5. And I'm just highlighting that at each redshift, the samples use a different set of line ratios to determine the metallicities. And that lack of uniformity is introducing systematic uncertainties of this comparison at different redshifts. So we'd like to be more careful with all of these things to improve metallicity studies at high redshift. And that's something that we've done in our recent work. So to overcome the difficulties with sample size and with spectral quality, I'll be using data today from the MOSDEF survey, which is the MOSFIRE Deep Evolution Field Survey. This was a large program on Keck that lasted 4 years and had about 50 nights of observations on MOSFIRE of galaxies at redshift of 1.5 to 3.5. It's a rest frame optical magnitude limited sample. And it's in the candles fields, which have a lot of multi-wavelength data where we can do good SED fitting for robust stellar masses. And you can see in the bottom here some examples of some spectra along with the SEDs of galaxies in the sample. You can see these beautiful emission lines we detect with 2 hours per filter depth with MOSFIRE. And if we take a look at some numbers here, the survey measured redshifts for about 1,300 galaxies. And so we have several hundred galaxies in 3 different redshift bins that we can look at in the MOSDEF survey. And in particular, I'm going to be focusing on the redshift 2 and redshift 3 bins, these 2 higher bins in this study. So this gives us really good statistics and also a representative sample, as I'll show. Just wanted to highlight that the reduced science spectra are actually publicly available, and we'll be releasing our catalogs of emission line measurements and other derived quantities soon. So if you want to use these for your science, feel free to contact me or check out the website there. So we get both a large and a representative sample from the MOSDEF survey. Here I'm showing the sample at redshift 2 and redshift 3 I'm using for this work. These are star formation rates derived from H alpha and H beta at redshift 2 and redshift 3. You can see we're dealing with samples of a few hundred galaxies in each bin, which is a big improvement to samples of, say, a few dozen in past studies. And you can also see that these are representative. I've shown in the dashed lines the star-forming main sequence as determined from Spiegel et al. 2014. And you can see that our sample is also representative. These are main sequence galaxies at these redshifts. Now, about how we measure the metallicities, we also want to make improvements there. And we've been very careful about the way we do this to really eliminate systematics and get the best measurement possible. So first, we use a uniform set of emission lines at all redshifts. At redshift 0 and at the high redshifts, we use the lines of oxygen 2, neon 3, H beta, and oxygen 3. These are all alpha elements, the metal lines, which is quite nice. When you use nitrogen, you have to worry about the nitrogen to oxygen ratio, which varies as a function of different properties and might introduce systematics. And so we use a uniform analysis of emission lines at all redshifts. And then a really important thing that we've done for the first time in this work is that we use different metallicity calibrations at redshift 0 versus at high redshift to reflect the evolution of the ionization conditions in the ISM that evolve with redshift. And in particular, we see evidence for this evolution through things like the evolution of the BPT diagram sequence. On the right, I show the BPT diagram, O3 over H beta versus N2 over H alpha. And the redshift 1.5 and 2 galaxies that are the colored points here are actually offset from the sequence of star-forming galaxies at redshift 0. And this reflects a change in the ionization conditions of the ISM. What that change is driven by is an entirely different talk, and I'm happy to discuss that with anyone in a meeting, but I'm not going to get into it today. But what I'll say is that those changing ionization conditions change the form of metallicity calibrations. And so we shouldn't use normal redshift 0 calibrations for high redshift data sets. And so in particular, what we use is these calibrations based on extreme local galaxies that are analogs of redshift 2 galaxies. They've been selected to lie in the same region of the BPT diagram as the redshift 2 sample. And in fact, we've used a small number of redshift 2 galaxies that have direct method metallicities to verify that these extreme local calibrations actually work at redshift 2. And so this should give us more accurate results at high redshift than the usual approach, which is to apply a normal redshift 0 calibration to all the samples at low and high redshift. So getting through that, we can go ahead and turn to results. So here's what we see for our measurement of the mass metallicity relation using this approach. On the left at redshift 2 and on the right at redshift 3, we have a number of individual galaxies. You can see our detection rate for the emission lines is quite high, down to 10 to the 9 solar masses. So we're fairly complete over this mass range. And then I also show stacks in bins of stellar mass to look at sample averages, which you can see in the larger data points there. So if we put this all together, we can start to look at the evolution of this relationship with time. So I'm showing here from redshift 0 up to redshift 3, the mass metallicity relation. We find some really interesting things here. First off, we find that the low mass slope of the mass metallicity relation is actually remarkably redshift invariant. And this is something that a lot of earlier studies didn't see because of different biases in their sample selection or the way they were determining the metallicities. And so we find that metallicity is proportional to stellar mass to the power of 0.3, which is very interesting. That's close to the scaling you expect from momentum-driven winds controlling the shape of the mass metallicity relation. This constant slope with redshift suggests that the same physical process controls the shape of the MZR over the past 12 billion years. Now, as far as the evolution of the normalization, we find a fairly slow but steady evolution. It's about 0.1 dex in metallicity lower per redshift is what we find. This is consistent with what's seen in modern cosmological simulations such as Illustrious, Fire, Eagle, and Mufasa or Simba simulations, which is interesting. So we take these results and I'm going to apply the equilibrium chemical evolution models to them, and then we can put constraints on the mass loading factor, which is really what we're trying to get at, is understanding the outflows in these galaxies. So here we show the mass loading factor as a function of stellar mass as derived from our constraints on the mass metallicity relation. And we find again that the scaling of the mass loading factor with stellar mass essentially shows a universal low mass slope that doesn't evolve with redshift. And this again is similar in slope to what's seen in cosmological simulations. It's especially interesting that it matches what the Fire simulation sees, because they produce their outflows essentially self-consistently from physical processes instead of inputting a prescription for the scaling. And so that's quite an interesting case that we match that. We find that at fixed mass, the mass loading factor actually increases as redshift increases. And so this tells us that as you go to higher redshifts, the efficiency with which outflows are removing material from galaxies is actually higher. And so that has implications for outflows actually being more impactful as you go to earlier times. Now, one question we could say is what is controlling the slope of the mass metallicity relation here? Is it the metal removal mechanism or the metal dilution mechanism? And to answer this question, we can compare the mass outflow, the mass loading factor with the gas fraction, which is shown in this plot here, the ratio of the two. And we find that at all redshifts, the mass loading factor is larger than the gas fraction. And this tells us that it's actually the outflows and the metal removal mechanism that is the dominant driver of the shape of the mass metallicity relation at all of these redshifts. But you can see that in our high redshift samples, the ratio of the mass loading factor to the gas fraction is actually much smaller than it is at redshift 0. And so if we extrapolate this trend, we might reach a case around redshift 5 or so, where actually the metal dilution mechanism takes over as the dominant mechanism in regulating galaxy metallicities. And so measurements with James Webb at redshift 4, 5, and 6 is going to be really interesting to understand whether or not that takes place. And finally, is the normalization evolution due to metal removal or metal dilution? And here what I'm showing is a plot where we've broken down the evolution from redshift 0 to redshift 2 into the fraction that's due to metal removal and the fraction that's due to metal dilution in these two different colored lines. And you can see that each mechanism actually accounts for half of the normalization evolution. And so both of these, the change of both of these mechanisms with redshift is important to explain the full evolution of galaxy metallicities. Neither dominates. So now I'd like to talk a little bit about this 3-parameter relation, the fundamental metallicity relation between mass, star formation rate, and metallicity. So a big question is whether this relation evolves with redshift. When it was first proposed by Filippo Minucci in 2010, he presented some tentative evidence that this FMR does not evolve with redshift out to redshift 2. And so now we can test this hypothesis with much greater precision with our more recent measurements. So what I'm showing here is essentially the FMR in a few different ways. On the left-hand panel, you can see here metallicity versus stellar mass, color-coded by star formation rate. Again, you can see at fixed mass, higher star formation rate means lower metallicity. On the right, this is a different projection of the same relationship where the x-axis variable is now a linear combination between star formation rate and mass. And it's chosen, so the coefficient for star formation rate is chosen to minimize the scatter in this relationship. So you can see it becomes essentially a one-dimensional relationship in this projection. And then in the bottom, I'm just showing the metallicity residuals with respect to a best fit. So you can see the residuals are very small, much less than 0.1 dex. So if I now overlay our redshift 2 and redshift 3 data on this plot, you can see that they actually perfectly follow the redshift 0 FMR. So it seems like the FMR does not evolve with redshift really at all. I mean, to very high precision. We find that the evolution must be less than 0.04 dex in metallicity from redshift 0 to redshift 3, which is essentially negligible compared to our measurement uncertainties. So this is really interesting. So what are the implications of this non-evolving FMR all the way out to redshift 3? Well, one thing it tells us is that galaxies must stay near what we call the equilibrium condition as they grow. So this equilibrium condition is given by this equation here. It basically means that the accretion rate is very well balanced with the star formation rate, the outflow rate, and also the change of the gas mass of the galaxy with time. And essentially this means that SFR and outflow rates quickly respond to gas accretion events, essentially on the timescale of a dynamical timescale. And this is quite interesting. So it tells us that essentially the way that baryonic growth happens has been proceeding in the same manner all the way out to redshift 3. And an easy way that you can model a non-evolving FMR is essentially by requiring that the gas fraction and the mass loading factor of outflows as a function of star formation rate and mass do not evolve with redshift. And if it's true that these particular parameters as a function of mass and star formation rate are redshift invariant, that's actually really powerful to form a redshift invariant framework that can describe the growth of galaxies. So the question is it realistic? Do observations suggest that these two parameters as a function of mass and star formation rate don't evolve with redshift? And I would say there's some preliminary evidence that yes, this might be the case. So on the left side, I'm showing gas fraction as a function of this x-axis variable is the offset in star formation rate relative to the redshift 0 star forming main sequence. So I'm showing both the high redshift data in black here, and then redshift 0 data exists in this box down here. I haven't shown the redshift 0 data, but this red line is a fit to the redshift 0 data, and I've extrapolated this out to overlap with the high redshift data. And we can see from this comparison that at least in a rough sense, the gas fractions of the high redshift galaxies fall on an extrapolation of this relationship that's fit to the redshift 0 galaxies. And so this suggests that gas fraction as a function of mass and star formation rate does not strongly evolve with redshift, which fits the picture I've just painted. On the right-hand side, I'm showing measurements of the mass loading factor from redshift 0 galaxies. So these measurements are made directly from modeling rest UV absorption lines at redshift 0. This is work from Tim Heckman and John Chisholm. And I plotted these again against the same variable, this offset from the redshift 0 star forming main sequence. And you can see that there's a positive correlation here. It's a bit loose because the error bars are quite big, but when I bin it up into 2 bins and take sample means, you can see in the black points that there is a relationship here. The red line that I plotted on here is the correlation between these properties that we would need to have a non-evolving eta out as a function of mass and star formation rate, which is essentially consistent with the preliminary correlation we see between among the redshift 0 data in this parameter space. So that's quite interesting, and it might indicate that this is actually the case. And I'll just quickly mention that there is some theoretical work that has suggested this is the case as well. And it suggests a fundamental connection between the gas fraction and the mass loading factor that would explain why these things don't evolve with redshift. So this is some analytic theory work from Chris Hayward and Phil Hopkins from a nice paper back in 2017. And they basically did analytic theory for outflows in a turbulent ISM. So a turbulent ISM has a range of densities that's regulated by the energy input and the feedback in these galaxies. And the energy injection from supernovae can blow out gas as outflows if that gas is below a critical density in the ISM. And the important thing they found is that the fraction of the ISM that is below this critical density increases with larger gas fraction in the galaxy. And that's shown by this, this plot on the left, where the eta turb, which is essentially the outflow mass loading factor, it is larger when the gas fraction of the galaxy is larger. And so this basically corresponds to a situation where the eta out is larger when the star formation rate is larger as well, because of course the gas content and the star formation rate are going to scale essentially linearly according to the Kinnigan-Schmidt law. And so in this case, the FMR emerges naturally because if you change the gas fraction, you simultaneously change the star formation rate, but you also change the mass loading factor because of this connection between mass loading and gas fraction. And so really we need to pursue this theory a little bit more to understand how holistically this can describe what we see in the FMR, both at redshift 0 and at high redshift, to see if we can establish whether this redshift invariant framework for baryonic growth is actually what we're seeing here. So I think I'm running out of time. I'm just going to say really quickly, because it's exciting, there's a lot of exciting prospects for measuring metals in the epoch of reionization. We know that very high redshift galaxies are not pristine. They have metal enrichment because we see strong dust continuum emission, and we see detections of strong emission lines like carbon-2 and oxygen-3 at 88 microns as detected by ALMA in these galaxies. And so James Webb's going to do a lot of exciting things. It's going to measure rest optical lines that we can use the line ratios to determine metallicities. But we still have this question about, what metallicity calibrations will be appropriate at redshift 6. And it's not clear that the ones at redshift 0 or redshift 2 will be appropriate at redshift 6. But a really exciting prospect is that we can actually do direct temperature-based metallicities at redshift greater than 6 by combining ALMA and JWST. And in particular, you can combine this oxygen-3 88 micron line that's been detected for several sources at redshift 6, 7, and 8 with the rest optical oxygen 3 line as measured from James Webb to infer the electron temperature and get these direct method metallicities. And so we wrote a paper on this recently at UC Davis, led by Tucker Jones. We basically used some preliminary constraints from Spitzer IRAC imaging and HST imaging, and combined that with the oxygen 3 88 micron measurements from ALMA to place preliminary constraints on metallicities at redshift 8 using this method. And so it's a very exciting thing. And in fact, we found out just, I guess, was it last week that the JWST results came out that we actually got a program improved that's led by myself and Yuichi Harakane that's going to be measuring rest optical lines for 3 of these sources that already have oxygen 3 88 micron measurements from ALMA. And so those will actually give us the first robust metallicity measurements in the epoch of varionization that will form essentially the foundational framework that through which we'll understand the metallicities from other measures at those high redshifts, such as the strong line method. So those are some really exciting prospects. So I think I'm out of time here, so I'll go ahead and stop and wrap up there. But I just want to say, I hope that what I've shown you today has demonstrated that the study of galaxy metallicities, especially at high redshifts, is moving into an era of essentially precision studies. We're really getting past systematics. We have very good data and very good statistics now, and we're starting to do a much better job addressing these systematics to get to a precision study where we can really trust the inferences on gas flows that we get from the metallicities. And with James Webb launches, we're going to carry that right up into the earliest times where we can understand the formation of the very first galaxies with these same methods. So thank you. I'll take any questions.
Great, thank you for that great talk. We can take questions now. So if you have a question, just use the raise hand feature, and I will, I'll call on you. Okay, Charlie.
Yeah, that was a great talk. Thanks. Can you talk a little bit more about how you've dealt with systematic uncertainty, the calibration issue with metallicities? You kind of went over it quickly, but can you tell us about how you've dealt with that?
Yeah, absolutely. Let me just move back to that slide real quick here. Yeah, so the calibration issue, I mean, essentially the way we get redshift 0 calibrations is that you have small samples where you've measured metallicities through what we call the direct method or the temperature-based method. And to do this, you have to measure these weak auroral emission lines like oxygen 3 at 4363 angstroms. These are about 100, 200 times weaker than the strong lines like H alpha. And so it's very difficult to measure these, but you essentially, for a small sample, you measure this direct method, and then you have the measurements of the strong line ratios like N2 over H alpha or something. You plot them, you draw a line, you get a calibration. Now at high redshift, this has been a struggle because I mean, it's hard to detect these weak lines at high redshift, but we've been slowly building up a sample, and that's what this red sample is here. So it's a sample of 18 galaxies with direct method metallicities at redshift 2. And you can see the sample error bars are large in many objects, and it's certainly not large enough to draw a line through and say, I have a new calibration. And so the approach we've been taking is to take the sample average and compare that to different calibrations that we form from lower redshift galaxies. And so it's via this sample average, which is the black point here, compared to this green line, which is this high redshift analog calibration that's given us confidence that these local analogs are actually producing calibrations that are applicable at redshift 2. We've been continuing to do work with deep Mossfire spectroscopy to expand the sample. We have about 5 or 6 more galaxies to add to this plot from the past couple of years' observations. But ultimately, we're going to need James Webb to really break this open and make a calibration that's only based on high redshift. But the exciting thing is that we actually got the time to do it. So Alice Shapley and I PI'd a proposal that's been awarded 64 hours to measure these auroral emission lines for 50 galaxies at high redshift. to much higher signal to noise than we have here, and over a larger range of metallicity. So, once we get that from James Webb, we can actually forget, which local calibration is appropriate to apply at high redshift. We could just make one at redshift 2 and sort of be done with the whole situation. So that's, I guess, the bright future that's going to be coming in the next few years.
That's great. Thanks.
Rohan?
Thanks, Ryan. This is really fantastic. So in a similar vein as the previous question, I was curious about the fundamental plane stuff you were showing that lines up very neatly.
Yeah.
So I was curious how the star formation rates are computed for that particular plane. Are all of them H alpha, or are they UV, or are they mixed? Like what's, how are you measuring SFR specifically?
Yeah, that's a great question. So everything is from Balmer lines, dust-corrected Balmer lines. So redshift 2 and redshift 0 are from H alpha. And at redshift 2, we have H alpha to H beta to do our dust correction. So those are quite robust. At redshift 3, we only have H beta. But we've essentially, with the redshift 2 sample, we've calibrated a relationship between the Balmer decrement dust correction and the SED fitting results. So the SFR and the AB from SED fitting calibrated a relation to get the EB minus V gas based on H alpha and H beta. So that's how we got that. So we were certainly as consistent as we could be with the data.
Great. We probably have time for just one more question. Any other questions? Okay, I think we're all out of questions. Let's thank Ryan again for an excellent talk. Also, if you'd like to chat with Ryan later today, in the email I sent, there is a schedule. So I think there's still some slots. So please feel free to schedule some time to chat with Ryan. And unfortunately, the other speaker had to cancel this week. So this is it. So have a great rest of your day. And we'll see you guys online next week. Bye, everyone. Thanks, Ryan.
Thanks, everybody.